SIMM webinar in 2021. I'm a Chief Engineer in the Pyrometallurgy Division at Mintech, and I'll be chairing this webinar. Thanks to all the attendees for joining in this afternoon for this exciting webinar. I would like to take this opportunity to introduce today's speaker, Mr. Alastair Macfarlane, who is an expert in mining. His inspiring career spans for just under 50 years. He graduated as a mining engineer in 1973 from Combone School of Mines, located in the UK, whereupon he came to South Africa, joining Anglo-American, and after several international assignments, he rose to mine manager and consultant in minerals resource management at Anglo Gold. He joined Wits University in 1999, where he worked as a senior lecturer, lecturing mining-related courses to undergrad and postgraduates. During this time, he developed numerous new courses and programs. He has consulted to many companies locally and internationally in areas of mine optimization, mine planning, and mine feasibility. Alastair is a non-executive independent director of Implats and is a past president of the Southern African Institute of Mining and Metallurgy. He has also served on the Council of Association of Mine Managers of South Africa. Today's talk, ladies and gentlemen, is entitled Dilution Control. The webinar will cover a broad description of the impact of dilution on various mining methods and means to control and measure dilution. This will focus mainly on the define, design, and raw aspects of dilution control. And for your information, ladies and gentlemen, the presentation will be circulated to the participants, and please kindly ask your questions under the Q&A tab and not on the chat, as we could miss your question. Over to you, Mr. Macfarlane, and looking forward to an educational presentation. Thanks.
Thank you, Butle. Let me get my screen up if I can. Can I just ask if that's visible?
Yes, that's visible. Go for it, thanks.
All right, great. Thank you, Butle, for that introduction, and good afternoon, everybody. I'm going to talk to you today just about dilution and really, cause and effect of dilution as just one aspect of the whole area of mineral asset management. And I'm going to be fairly general because I'm going to cover a number of different mining methods as to how it's applicable in each of those. So let's just go back to start with back to our good old friend Samrek, and understand Samrek talks to us clearly about how we convert mineral resources to mineral reserves, and historically we always did that by applying the modifying factors which are listed here, and in particular the mining modifying factors for this talk. But as changes happened, I think from as far long ago as 2008 now, Samrek requires us not to just apply the modifying factors, but to produce a life of mine plan, or at least a pre-feasibility study. And within that, of course, we apply our modifying factors in the planning process. And in terms of mining, those would be about things like the effects of the mine design, dilution, mining recovery, mining widths, mill widths, percentage extraction, and production rates. So it's an essential component of our mineral reserve classification. So from a survey point of view, we go back to looking at our different widths, typically in our tabular mining environment, where, Stora talks to us about channel widths, which we know is the width of the reef that we're looking at, then looking at our stoping width, our broken width of what we actually take out, converted then into a tramming width with the addition of fall of ground material, and also ore pass scaling and that sort of thing, through to a hoisting width, and finally to a milling width. And so we'll have some increase from a channel width of 40 centimeters, perhaps up to 180 centimeters on milling width, when we bring in all of this dilution that occurs along the process. And we'll be looking at that as a plan and an actual. And in survey terms, the difference between the plan and the actual would be a discrepancy, either positive or negative discrepancy. In this case, negative discrepancy. So dilution is contamination of ore with barren waste wall rock, typically, or it may be contamination of ore with material below the cutoff grade. So therefore, we need to know where the cutoff grade is in order to classify that material either as ore or as waste. Ore is marginal material. It could also be contamination of ore with recovery reducing minerals, especially in the base metal environment, or even in the PGM environment, where excess chrome could be reducing downstream our recoveries. And although we may be able to separate it out and sell it as a saleable product, it's essentially, if it's reducing recovery downstream, then it's diluting material. And dilution can be internal or external. So here are some definitions. Dilution, the tons of waste compared to the tons of ore. Sometimes you see it that it's tons of waste compared to tons of ore plus waste, but that's not correct, because that one tends to underestimate the dilution. So it's a percentage of units of dilution compared to units of ore. And primary dilution is inherent in the mining method selected, whereas secondary is dilution incurred beyond the planned stope dimensions. So total dilution is primary plus secondary. So starting off with a tabular environment, if we have a look at potential dilution that's coming in through mining through fault losses, dikes and faults, bringing in overbreak, things like that, off reef down here, how much we're pulling in from in-stope excavations. There's an interesting question down there. It says, what is the effect on mine call factor? And there was one operation that I looked at fairly recently that had a pretty poor mine call factor, and it was quite clear in that particular case, because of an extremely high propensity of this kind of thing, that the main cause of the mine call factor there was underestimation of this kind of off-reef contamination in the ore flow. But that's only for that particular operation. We also looked at others where the opposite was true, where we found that the amount of dilution from this kind of thing was already accounted for. So it's really a case-by-case situation. So again, in a tabular environment, we have planned stope dimensions for a channel width and a mining width to accommodate people to go in there to be able to drill and blast. And obviously we want that to be minimal, but we may get unplanned footwall dilution here, especially where we've got soft footwall, where we may be pulling out things like Boyson shale, that sort of thing in the footwall. We may have damage to the hanging wall. We're bringing in waste from the hanging wall beyond the planned dimension, maybe a bit of underbreak over here, and then internal dilution as well, which would relate to split reef. And I'm aware of a couple of operations at the moment that are battling with split reef, where this material is causing significant dilution, and attempts are made to do things like waste packing and separation, but from a more advanced technology point of view, you know, one could be looking there at things like ore sorting technologies, which have advanced quite well in recent years. Another picture based on a real case there. We can see where our ore boundaries are and some split reef and internal waste here. Waste in the footwall for access and overbreak in the hanging wall. So dilution sources in tabular mining during stoping will typically come from, you know, overcharging, over drilling, inaccurate drilling, good old-fashioned stuff that we've tried over many years to try and overcome with better explosives, with also drill rigs and anything else, other kind of technology that can help us there. Falls of ground, impacts of seismicity, scaling in ore passes and other excavations, and cross-tramming. And then after stoping, stope hanging wall failure, like we see here, where there's our channel width or our reef or our planned stope width. And this is a typical backbreak situation in a PGM environment, where all this material here, which is falling down there, will either result in abandoning of the ore that's underneath it, or pulling out very significant dilution. So we can get ore loss as a result. Maybe ore pass failure occurs as well. Watch out for belt changeovers, because we may get their waste being hoisted or put into the plant, or vice versa, reef going on the waste dump. Main ore pass scaling and deep operations and surface cross-tramming as well. So these are just some of the impacts that we'll get. So fractal analysis and survey measurements should be able to provide calibration for us for these forms of dilution. So accurate measurement and data capture and data analysis is more possible these days, and we need to utilize it in order to calibrate our ore body to be able to be putting the right factors into our planning. Typically in that environment, you know, very highly fractured ground that can, you know, result in obviously a lot of dilution coming out here that is unplanned from our planning model. So let's move just away from there into massive stopes. So starting off with sort of sub-level open stoping environment, we can get dilution coming in from sidewall failure if the dimension outside of our planned stope is into waste. So we could get sloughage happening here on both sides. From our blasting, we can get damage caused there, drawing in waste by over-drilling, vibration and overcharging. We might have internal dilution such as this that's reporting down to the draw point, because in this kind of environment we cannot be selective. So whatever is in there is going to come and report through to the draw point. We also get time-dependent failure here. If we're mining this kind of stope on a retreat, time-dependent failure will also result in sloughing of sidewall reporting to the draw point where we may be still drawing. Obviously, poor sampling can also impact on this if we don't understand well enough where our ore boundaries are, and over-drilling, inaccurate drilling, overcharging of these large blasts, creating vibration, poor geological and geotechnical models, which the accuracy of which depends on the quality of the delineation drilling that we are doing underground. For stope design, maybe poor grade control, internal waste or low grade, out of sequence draw, which I'll show you some examples of just now. Perhaps if we're doing post backfill here, backfill collapse and poor draw control down at the draw point, and out of sequence draw as well, resulting in premature dilution entry. Sometimes equipment sizing, looking at equipment that is too big, where we have to make larger excavations to accommodate the machine, that is not good, and maybe the wrong mine design and wrong mining method altogether. So clearly on the drilling side of things, this is more prevalent in narrower ore bodies, and you know, if we're looking at the copper belt, typically in Zambian operations, where we looked at the larger operations there, they would have been mining very large ore bodies where dilution is not a significant issue. Whereas the narrower the ore body becomes, as has been the case with a number of the newer operations up there, then dilution becomes much more critical, because 10% dilution at the edge of stopes on a 150 meter wide ore body is fairly insignificant. But if the ore body comes down to a 5 meter width, 10% dilution on that becomes highly significant. And would be exacerbated if the ore body boundaries are irregular like this, and we're getting blast vibration. We have weak side walls here, then a hanging wall and footwall. Then we have over drilling. We can get more and more dilution reporting down to the draw point. The one particular one that we were looking at was about a 4 meter wide ore body with ring drilling like this. And the ore itself, as well as the sidewalls, were weak to the extent that after drilling the holes, sometimes the holes were closing up because of the highly fractured nature of the ground before we could get the explosives in. It was a different challenge. So obviously drilling control is highly significant here. Directional drilling, knowing the end position of the drill hole is critical, and we can do that by directional control on the drill rig. We can also do it by microseismic monitoring. It can actually pick up where the drill bit actually is in real time, and we can compare that back to our model. But that, of course, then you know, needs us to have an accurate model as well. So a lot about data, and then we can design our ring pattern accordingly. We could be getting dilution in terms of mining-induced stress and fill failure, like I said before, and the time-dependent failure effect also. So here we are, thin ore body, vertical ore body in an open stope. That's our planned ore to come out there, and you can see here you've had severe sloughing happening here on both hanging wall and footwall, probably resulting in a good 100% dilution if you just look at the dimensions there. And this is time-dependent failure. This will all report down to the draw point and cause dilution. So we need to get the broken ore out as quickly as possible before this time-dependent failure happens. So when it does report, you would see here the material that we are blasting here, if our blast pattern is right, apart from the different coloration of ore compared to waste, the fragmentation is different in terms of what's reporting down there. So this kind of sloughage, when it's reporting to the draw point, ought to be quite clear to the operators or the supervisors when it reports there. But if you're chasing tons, they may be blind to that. Here's a very complex ore body that we had a look at, where they had a severe problem with mine core factor, and this here you can see that on a particular sub-level, the ore body in red. This is a plan, and delineation drilling that's been done to try and identify the ore boundaries. But this is extremely irregular, and massive dilution happening here. To try and mitigate against that, these sub-levels in this sub-level open stoping operation were minimized to only 8 meters separation vertically. and or on the subvertical, to try and overcome or minimize the effect of the extremely irregular ore body. And here you can see an overhand layout for this ore body. And the secret here is to get the ore out before the time-dependent failure happens. And in this particular case, they were not doing that. They'd gotten severely out of sequence down here. So there was massive dilution reporting to the draw points, resulting in severe drop in recovered grade. So we look in the block cave situation. We are looking at either low-grade material reporting that is actually inside, because we can't be selective here at all, maybe low-grade material within the pipe, or different fascies of low-grade material. Dikes and sills that may fail, like was the case at Cullinan, the Gabbro sill that was intended to stay in place but eventually failed. Sidewall failure occurring either in the block itself, or sidewall failure from the open pit above, reporting down onto the top of the block. For this kind of thing, we need to have a shut-off grade policy at the draw points on the production level down here, and that needs to be based on draw curves, which we'll talk to you later on, or on simulation of the draw. In the sub-level caving operation, we've got caving material. We're mining on the retreat here, uphole ring drilling, multiple sub-levels, and in years gone by, typically we would have had isolated draw. We'd be working on one level here, trying to pull ore out from one or two draw points or sub-levels, and the result would have been pretty high rates of dilution reporting in there, maybe 20, 30, 40% dilution. These days, what we work with is interactive draw. So we work multiple sub-levels at the same time, both in the vertical dimension and in the strike direction, so that effectively we have a moving curtain of ore all the time across multiple draw points. And we also rely on the fragmentation here because fine material runs faster than coarse material. So in this case, we blast the ore to fine portions, and we make sure that we're pulling that out as quickly as possible, and it comes through before the waste reports. And with multiple draw points, as I say, we have effectively a moving curtain through there. So blast design helps us here, and what we can also do, if we want to get really clever, is to actually, with the blast here, actually create concussion onto the waste to temporarily delay it coming through into the draw points. So these days, this method, we can probably bring our dilution down to 5 to 10%. In the open pit, if our ore boundary is, sorry, I'll just plug in. If our ore boundary is irregular and not quite matched to our bench profiles, then that will draw in dilution. We may, of course, as well have internal dilution. And then we also need to look at blast movement, whether it be waste, which can cause spillover on our benches, onto our ore floors, or movement of the ore itself. So we need to be able to model that, and that we can do. We can put in markers to check out on that ore movement as well, so that we had an original dig plan, which was looking something like that. And by the time that we blasted, then that ore has moved, and we can go back and recalibrate that dig plan in order to make sure that we're going to get going to get minimum dilution and minimum ore loss once we start loading. Also, you know, we need to look at selectivity. Important to say if we want to increase selectivity because we want to be, say, for example, here, cutting those benches into half size for better control on dilution, then you've got to ask the question, is the equipment that we've got matched to the level of selectivity that we want to apply? That's often something that precludes you from doing that because you don't want to have to replace your whole fleet. There's a bit of a trade-off involved there. Here are some typical percentages of different mining methods of dilution in South African mines, between unsupported methods like sub-level open stoping, benching, those kind of methods, compared to where we're using artificial support, where that artificial support may be specifically applied, obviously, for dilution control, like in the case of cut and fill operations. Here's some international comparisons that have been done. There you see sub-level caving down to, in these cases, they said 10 to 30%, 10 to 15, or 20 to 25, where these days we can reduce that below those numbers. This is an example, a Golden Giant gold mine in Canada, where they've done stope calibration and back analysis. So here are all different stopes in a sub-level open stoping environment with backfill or post-backfill. And here are the planned tons to come out from the stopes. Here are the actual mined tons. And these actual mined tons are taken from obviously draw point tons measured, as well as cavity monitoring that's done afterwards. And there you see, for example, this stope here was planned 60,000 tons and actually drawn 104,000 tons coming out of there. So a lot of hanging wall waste failure happened in that particular one there. That came from the cavity monitoring that identified that. And on another one, this one up here, you'll see there the tonnage drawn was a little bit more than planned tons, but there was 13,000 tons of backfill came out of that draw point there. And so here you see the draw point, the dilution, so 34% in that case, 70% in this case here. So this information is useful to you. It's historic, obviously. You know, you can't change that. But on the other hand, what you can do, depending on the geozone that you're in, you know, you can say, let's redesign, because clearly something was wrong in this case here with our design. Let's go back and have a look at that. Must be that our stope dimensions are not correct. Something has changed, something has gone wrong. Let's make sure we take account of that, or on these with a 20% or, you know, 34%, what went wrong. And let's incorporate that into future designs. So when we talk about dilution control, we talk about define, design, and draw. So defining is making sure we define our stope boundaries, our geological and geotechnical characteristics. So that's all about data and modeling and surfaces and everything like that. Design, looking at designing stable stope dimensions, designing drill and blast patterns, and cable bolting and other support solutions. And draw, ensuring timeless draw control, monitoring our draw tonnage and grade in real time, and reconciling and back analysis all the time. So talking about define, we have done our delineation drilling underground, and we need to make sure that the data that we're getting out of that is sufficient in terms of the end point spacing of our fans of delineation drilling, so that we're getting good ore boundary definition that we can use then for stope design. We need to define our data requirements. What data do we need? Well, obviously we want grade, but we want structure, we want boundaries, and we want geotechnical characteristics such as these, which we're going to use for defining mining rock mass ratings. So we're going to be looking at intact rock strength, rock quality designation, joint spacing, fracture frequency per meter, joint condition, and we've got ratings on each one of those. We have a choice here of either saying let's use rock quality designation and joint spacing, or just use fracture frequency per meter. So this comes from physical observation and measurement, and these are ratings. We add them together to come to a rock mass rating or a rock mass strength, and then we put in adjustments for weathering, orientation of the stope, induced stresses, and blasting effects to give us a mining rock mass rating. And we'll see how we use that a little later on. That's input into either empirical or numerical modeling to predict dilution and then to do stope design. So when we do stope design, first thing, mining method selection, maybe a bunch of trade-off studies we need to do, saying, what are the expected dilutions that we're going to get, and depending on mining method and stope dimension, what's the level of selectivity we can apply, ore loss, what's that likely to be, and obviously cost of it. Mine design, we look at our drift design and our bench heights. In this case here, we've got a comparison between for cut and fill methods using standard drift development for cut and fill or drift and fill. And we can modify that. This is a fairly narrow ore body, so we can modify that by going to a shanty back system over here, modifying the shape to try and reduce the planned dilution here. Here are the outlines that we get, so that would bring in the unplanned dilution as well. Equipment selection, we need to look at size and our ability to be selective again, and then drill and blast, design for the correct hole size, powder factors, drill patterns, directional control, and our blast design in terms of whether we need perimeter blasting, explosive type, velocity of detonation, energy, etc. Equipment sizing, what we don't want to do is to create dilution to accommodate the machine. So get the right size machine to do the job and not to have to make a big excavation to accommodate it. And this just shows down here for different ore widths, the sort of dilution that we're going to bring in, where we've got a minimum stope width that we need for the equipment that we've got. And there we see the dilution coming from 700% down to 0% down at the bottom. And also for mechanized stoping, the minimum working widths that we need for different machines. So that's an important mining engineering consideration to get the right machines. So we look at the modified stability graph method for dilution prediction. Rock mass rating, we looked at mining rock mass rating before. If we look at rock mass rating, Bianevsky tells us this is how we can characterize or derive rock mass rating, where Q in this expression is the tunneling index number, and Q is defined like this. And so we can calculate Q when we know these parameters here that we can apply, and that Q number there comes down into our modified stability graph calculation down here, where the stability number N is modified tunneling index times 3 factors, A, B, and C, one being a stress factor, second being a joint orientation factor, and the third being a gravity factor. And this was developed by Yves Potvin. And it comes through into this, where we say here, the modified stability graph, here it is. Primarily, we would use it for defining whether, in terms of designing a stope in a massive mining environment, or any other environment for that matter, is it going to be stable or is it going to be caving? So we look at this parameter here called hydraulic radius and stability index here, where we've calculated it this way. And hydraulic radius is a term used in hydraulics and is a number derived by dividing the area of the excavation in question, whether it be the hanging wall or the plan area, multiplying or dividing that area by the perimeter for that particular surface. And with that combination, we can see where we plot for a given hydraulic radius. So we say, so what can we change? Well, we can't change the stability index because it is what it is. But the hydraulic radius, we can change. And we can change that by changing the dimensions and shape of the excavation or the stope surface. And so if we want to go into a caving environment, we can modify by moving this way. If we want to go into a stable environment, we go in that direction by changing the shape and plotting up here. So that we can do for basic differentiation, and there's a transition zone in the middle as well. But we can then move across over here, where again, with the hydraulic radius and the stability index, we can see where we plot in terms of this calibration, which is defining whether we get blast damage only, minor sloughing, moderate sloughing, or severe sloughing and potential wall collapse. And this we need to quantify. So we do that by calling it equivalent linear sloughage. And that means that sort of dimension. So we'll look at that in another graph. Before we look at that, here's again what we looked at just now. But here are the three factors: the A factor, the stress factor, the B factor, which is the orientation factor, and the inclination of the stope plane factor over here. So we just read those off from these calibration graphs. So when we talk equivalent linear sloughage, or equivalent linear overbreak or slough, it is equivalent linear overbreak compared to slough, volume of slough from the stope surface compared to the stope height times the wall strike length. So in reality, the kind of sloughage we'll get will have a profile like that. But what this is doing is it is converting that into a linear dimension across that stope surface. And so, you know, that going back to the graph, that says to us, what is it likely to be? Maybe we're in this zone. So saying we're going to get half a meter to a meter of sloughage across that stope surface, and that we can then convert into a dilution percentage, given our stope design. We can look at saying, well, let's try and tie this up so that if this is the hanging wall, we want to reduce the amount of dilution coming in, then we can tie it up by putting in cable bolts, a cable bolt pattern, which means to say we'll have to put in those hanging wall drifts to be able to do that, obviously all cost. And we can have a look here to say, we're knowing these numbers here about rock quality designation and joints and hydraulic radius. We can define for a particular combination of those factors for our ore body or our stope, and we want whichever condition we want, what is the cable bolt density that we require over here. And that's end spacing in terms of cables per square meter. So we can define that pattern for our stope for stability. As I said, obviously it comes at a cost. So there's a trade-off here. Is it worth doing all of that? Or do we tolerate the dilution? Or do we go to a different mining method? So those are cost-benefit trade-offs that we need to do. When we talk to draw, we're going to talk about dilution curves. Here's a dilution curve, courtesy of SRK. So here's the composition of our ore body over here, up to 100%. And here is the material drawn that we're getting at the draw point. So if we said we're going to get, we're planning 100,000 tons to come out of there, then because that's the tonnage in the block that we're looking at, then we would say at 100% draw, this is the point where I'm at, let's use this middle curve. Then I would say what I'm drawing out at that point when I'm at 100%, what is still coming out is 30% ore. So I'm not going to shut off there because I'm going to leave a whole lot of ore behind if I shut off at 100%. So I'm going to draw more than 100%, and I use the calibration curve to do that for me. And I can actually convert that into grade, and I can use that for grade control as well as dilution control. So I can say, I actually want to go to 120% draw because that's where I hit the cutoff grade over there, because I've converted it into a cutoff grade at when I'm drawing 20%. 20% of what's coming out is ore. The remaining 80% is now waste. So how do we get these curves? Well, it's back analysis. So we have to do it by measurement and collecting data so that we can develop the dilution curve, and we can then use the dilution curve to help us in our cutoff grade and our draw shut-off decision. When that material's coming down to the draw point, the diluting material may report prematurely if the draw sequence is compromised or if diluting material is finer. It will come down faster and report to the draw point. The diluting material may be visible. The shut-off decision should be taken on the dilution curves or simulations that we're doing. Grade control at the sample points is pretty unreliable, especially if you're getting this kind of stuff coming out at the draw point. So where we're looking at draw, comes back to the principle of either isolated draw at draw points or interactive draw zones. If we have isolated draw defined by the spacings of the draw points down here, and the size of the draw points and the height of the interaction, then what we may get is columns of ore left in the middle that don't report to the draw point. And we get rapid drawdown through the draw ellipse. And if we've got waste material above here and it's fine, like it would be from the bottom of the open pit, there's a lot of silt and stuff like that, it will race down through and will report quickly to the draw point, and we leave ore behind. Over here, if it's ideal, we get interactive draw there. And we're drawing all of these draw points in the right sequence and simultaneously, then effectively we have a curtain of ore that's lying at the top here, of waste, I should say, that's lying at the top and is moving down at the same rate as we're drawing. So we don't get the premature waste reporting down here. If, however, that zone of interaction is too big because we've put these draw points too close together, then we will funnel or rat hole that waste rapidly down through here, and it will report in both directions at the draw points. That's shown here, again, courtesy of De Beers, this one. Important interactive parameters are the draw zone diameter. We need to know and what happens, what is the interaction that we need to do, and spacings to avoid isolated draw. So it means to say we have to put our draw points closer together so that we get the correct level of interaction happening. Another parameter we need to know is the height of the interaction zone there in order to get the correct draw point spacing to minimize dilution. And here it is after another example. We may get ore loss and weight down onto pillars between draw points, which could cause geotechnical problem and draw point failure. And over here, as I said before, too much interaction, and we get dilution reporting very quickly and displacing ore at the draw points. We can do a lot of simulation on this sort of thing. As I said, fine material will tend to move down faster. So if that's diluting material, it'll get there faster than the ore. Isolated draw encourages early dilution entry, and we can use empirical design or simulation to define optimal layouts. This is just looking at a single draw point, but we could obviously simulate multiple draw points. And we've got markers in there that show us, if the waste is on the top, how quickly that waste is going to report down to the draw point. And we could simulate that for interactive draw as well. So there are some more dilution curves with a prediction there of dilution entry from that formula, looking at ore draw height times the swell factor, less the height of the interactive zone, times the draw control factor compared to the ore draw height multiplied by the swell factor. As I said, trade-off studies, cut and fill is a higher cost method, but it allows higher selectivity. You can drop the lower grade stuff down into the fill if you want. That relies on a lot of sampling though. In stope, sub-level open stoping is lower cost but less selective. Cut and fill is designed to reduce dilution in poor mining rock mass rating, hanging wall and footwall conditions. But the cost of the fill and the cyclicity of the operation must offset the higher dilution that you would otherwise get in the sub-level open stope. Sub-level open stopes can be designed for stability based on mining rock mass rating and hydraulic radius and the stability graph. And of course, for future stopes, you can change the stope designs if you're starting to get higher dilution entry as you go into different geotechnical and mineralized zones. There's a link which you can pick up. I'm not going to open it now, but you can pick up on once you get this presentation on the website. It's a nice webinar done by Australian Mining Consultants, AMC, and it looks at these kind of trade-offs here as well. It's about a half an hour to a 3/4 hour free webinar. So if you're interested, go and have a look at that. Other principles on dilution control would be try and expose weak walls progressively. Look at your drilling accuracy and shock and vibration minimization. Utilize cable bolting if it's cost effective. Pillar designs. Look at your extraction sequences. Backfilling, stope surveying, cavity monitoring systems to bring yourself down to a target of about 5 to 10%. What are the effects of dilution? What does it do? Firstly, it messes around your reserve block estimates. If your block estimates are assuming a particular dilution because it's a modifying factor and you're in fact getting a whole lot more, then your reserve statements are wrong. It skews numbers and results in over-evaluation. It disguises real problems because you might be measuring tonnage and thinking everything's okay, but then you look at your grade and you realize something is not okay. It displaces ore in the plant, which is a time value of money issue. It delays ore processing, and it incurs all the full mining and milling costs. And it maybe lowers your recoveries as well, because you're going to have more material reporting out to the slimes dam, and every ton of material that goes out there carries some value with it. And it decreases your cash flow and earnings. The effect on the cutoff grade, we've got a grade tonnage curve. Increased dilution increases the unit cost of metal production. That will increase your cutoff grade and move this line up. And as a result, your available resource or reserve is reduced. This reduces your payable ore reserve available, and increased dilution decreases the recovered grade. This further increases the cutoff grade. And if this happens unknowingly, then waste is being misclassified as ore. If you have a graded deposit, the principle of marginal costing and marginal extraction is quite important, because in an example like this one here, if this is your primary ore source here, M1, M2 is a secondary source, and both of those are economic, you want to take them out, and you've got M3 as well, which you want to take out. That material grades further into the hanging wall, and so where this may be your original planned stope boundary, and you would classify that as waste because it's below your break-even cutoff grade. If you look at an in-stope cutoff grade for a massive mining operation like this, you can actually carry on mining up to there on a marginal cost basis because you paid for all the excavation already with this material. So you could move forward there. So instead of classifying that as waste, it's marginal ore that can come out with this as well, and you can drop down to a lower cutoff grade and still be payable. This looks at cost savings achieved through dilution control at each graph represents a different capacity. And what you're seeing here is that if you take this line, let's take this line here, 500,000 ton capacity operation. This just shows the cost reduction or cost saving that you can achieve as you move down from 100% dilution down to zero. Quite significant. And this one I did on a simple model, just saying, 15% dilution compared to 30, just on cash flow. What do we get? Grade, drop in grade, obviously recovered. Process plant, slight reduction in process plant recovery. These are your ounces, your revenues, resulting in a 2/3 drop in cash flow annually in going from a 15% dilution to a 30% dilution. This one shows two graphs, this one percent dilution and this one percent mining costs. And what it's illustrating is if you look at the slope of the line, the impact on cash flow and percent dilution, we get that characteristic. And if we look at the percentage mining costs, we get that characteristic. So what it's showing is that dilution is giving a greater impact on cash flow than cost. That's interesting. But the reason is because dilution impacts not only cost, but it also impacts revenue. This is a long-term effect on a model that I had that I ran looking at impact on NPVs with increasing dilution. So when you get to 30% dilution on this, which was a gold mine model, you get to 0 NPV at 30% dilution. I kind of don't believe this model. It's a little bit too simplistic because there are multiple factors impacted by dilution. So I don't think it should be a straight line. I think it should be more exaggerated than that. This is looking at measuring dilution. So cavity monitoring systems that we can put in to stopes, open stopes once we've mined them out. There's our planned dimension. Cavity monitoring shows us that is the actual dimension that has come out of the stope. And we can build that into a 3D model and look at the surface of dilution over here on the stope. And we can use that for back analysis to say to us, this may be tolerable, it's not excessive, but if it is excessive, then we'll say there's something wrong with our designs. So for measuring dilution, obviously we can look at tonnage measurement compared to plan, grade at the measuring points in the ore flow to the model. So it means to say we have to have the correct grade measuring technologies in place, and we need to apply ore flow management and reconciliation in real time. So whatever the measuring systems are that we've got here, we need them to be giving us real-time information linked to our cavity monitoring system so we can do full reconciliation, linked to physical measurement, and looking at this all in a 3D real-time digital environment, so that we can take decisions on the fly where we see that something is going wrong. And we can do empirical and numerical modeling, and we can do simulation, back analysis, and constant calibration. When we look at constraints, dilution creates higher volumes at lower grades. Where constraints exist, either in the mine or processing or market, lower grade ore is fed through the constraint for longer. This reduces NPV and cash flow, and the opportunity is to reduce the dilution, thereby optimizing through the constraint. Alternatively, remove the constraint, and that's a cost-benefit decision. In other words, improve the quality flowing through the constraint and your ore flow. And we can look at a simple cause and effect. We look at effects of dilution, poor conditions, overbreak, bad ground, increased widths, increased tons, lower grades, resulting in poor recoveries, loss of capacity, increased costs of mining, poor safety, lower product coming out per annum, delayed ore to the plant, which affects, those two affect our NPV and also our cash flow, and so we get loss of shareholder or stakeholder value. And we look at causes that can be poor designs, wrong methods, poor blasting, poor process control. Those things based on poor information, not enough real-time data, maybe poor training and skills. And at the end of the day, blame ourselves, poor management resulting in that. Okay, so that is it. So thank you very much, everybody. So we can open for any questions.
Many thanks, Alastair, for that highly educational talk. There's currently only one question on the Q&A, so ladies and gentlemen, please, you are more than welcome to ask your questions. So let's go with this one question from Gangata Tabula. The question is, in a sub-level cave, what can be done to prevent too much waste fines from entering the cave? For example, waste can be slow into the cave and become ground down to fines in the cave over time.
Just a moment. I'm just going to make sure I can pick up the I can't open my Q&A. Sorry, could you just repeat that question?
Oh, okay. So in a sub-level cave, what can be done to prevent too much waste fines from entering the cave? For example, waste can slow into the cave and become ground down to fines in the cave over time.
Yeah, like I said, this is work that's been done in the last few years that says, if you typically your waste material coming in as hanging wall failure would be fairly large rocks, and it's true that as that moves down towards the draw point, it will grind, in terms of secondary fragmentation into finer material. But the secret is to be able to pull your ore out quickly. So that, you've also got a dilution curve at that draw point. So pull your ore out quickly by making sure that it's got good fragmentation that makes it flow easily. You can also, you don't have to have vertical faces, like on the graph on the picture that I showed, it showed vertical faces. You can also improve the rate at which that ore comes down by inclining those faces to more of an overhand configuration, and that will also help to bring that ore out quickly. And then the other thing is to get that interactive draw happening.
Okay, thanks. So the second part of the question then is on the technicalities. Do you apply dilution control similar to a block cave, or do you follow the draw control rules?
Well, you must follow the draw control rules, because that sequence of draw across those multiple draw points has got to be right, that you've got effectively got a moving curtain of ore on multiple draw points. You must get interactive draw as opposed to isolated draw, but it's in one plane, whereas in a block cave it's across 3 dimensions. So you've got to apply draw control as is required to make sure that you minimize dilution, and then apply dilution control by looking at what is coming out at the draw points, if you can get grade control and things like that working as well.
Okay, thanks a lot, Alastair, for that comprehensive answer. So the next question is from Mark. Can you explain how surface cross-tramming causes dilution?
Surface cross-tramming?
Yes, how does it cause dilution? Yeah.
It would cause dilution if you're mixing product on the surface. Let's say you're picking up. Let's say you've got a large complex where you're stockpiling, and then you're picking up from those stockpiles, and as you're picking up from the stockpiles, you're picking up dilution from the footwall. You may be cross-tramming ore and waste on surface where you've got a rail system that has multiple collection points and multiple dispatch points. Those are the kind of things that can happen. So you've got to have controls on your surface ore distribution to try and avoid that.
Okay, thanks, Alastair. So the next question is from earlier on in the presentation. You did mention SAMREC and the requirements that kicked in from 2008. Of course, also mentioning dilution. So of interest, how is the picture looking elsewhere in the world, in countries like Australia or China?
I can't talk about China, but because I don't know, but Australia, very similar. Our codes, whether it be SAMREC, JORC, 43101, all rely, they're all pretty much the same, in that regard, that they are saying that instead of just applying the modifying factors, you need to have at least a pre-feasibility study for a project, or a life of mine plan for an operating mine, and into that you factor the modifying factors. So they're all pretty much the same, and I guess the Chilean code is pretty much the same. So all the codes that fall under CRISCO are the same in that regard.
Okay, thanks, Alastair. You mentioned the availability and, of course, importance of data and data collection. Of interest, is big data of importance here, and what role does it play, if the answer is yes?
Yeah, there's multiple data that you need to collect here. So, there's all the data that we need for our designs. So just think back, there was a time when all those designs were done only on empirical models, and they were done manually. We are way beyond that now. We can produce 3D electronic models of our ore bodies. We can produce surfaces using things like Leapfrog and whatever else. But the accuracy of all of those depends on the data. So we need to make sure we've got enough data to feed into those models, to make sure that the models are reliable and representative, whether that be about structure or grade or whatever else. And again, we get to trade-offs to say how much data do we need in order to create a reliable model, and we don't have to collect too much data. Then from there, we need to look at saying in terms of our production data that we are collecting from our draw points, whether it be LHD bucket loads or weight fact, load cells that we've got on those vehicles, the positioning that we've got. We can look at destination, source and destination of ore, and we can integrate that into our model, and we can look at our ore flow management, looking at all the data we're collecting there on tons and grade, etc. And we can integrate, what we need to do is to close the loop on all of that so that we can go back to our model and we can say, how does what is actually happening compare to what the model predicted? And that closure of the loop can be done by integrating all of that data, lots of it. And then we can link that data to all kinds of other things, whether we want to bring in fleet management and engineering performance, whether we want to bring in costs, area costing, anything like that, to get real-time control through to a control room. These are the advantages that we've got now. But I think, the answer is yes, of course. Big data, we need to know what is the data that we want, how we want to integrate it in order to be able to make the right decisions on the fly in real time. But don't collect too much data. I don't want to collect data that we're not going to use, because that's not cost effective. So just a little caveat, let's not get sucked into the thing that, the more data, the better. There's a right amount of data to be able to do and make the right decisions.
So that excellent answer, Alastair. The next question is a follow-up question. With all the technology we have at our disposal, do you think dilution control practices in industry have generally improved?
Yes, they have, because like we said, with the sub-level cave, and with the kind of work that we can do in simulation on a block cave these days, technology has really helped us, because we can look at those, exactly what I just said, that whole big data integration and so on, and data collection systems, cavity monitoring systems and things like that. When we look at hard technology, there are those things that we can use as well. There's a lot of gaps in terms of, we've spoken about grade control. Trying to do grade control at a draw point is not easy or reliable. And there may be far too much variability on that data for us to give it credence, So there are some areas where we need research, and we need to find new technologies that will help us. Or proxies, if that's the case for grade. I think in some environments we're well ahead of where we were. In other environments, let's go back to our tabular mining environment. I think we've still got lots of work to do. To get better data. We know that survey data that's based on monthly measurement or stuff like that might be accurate on the day to an extent, but the day after it's not. So things are changing there, and we a lot of those things we're not really measuring, but it's a difficult environment. But let's think about mechanized room and pillar in PGM mining. There's a lot more data we can collect there. We can do cavity monitoring there on a real-time basis. We can understand the tonnage movement on what's happening with the machines. There's a lot more that we can do that we currently do. So, it depends on the situation, I think.
Okay, thanks, Alastair. So we are almost approaching 4:10 now. And then one very last question. One of the last slides, you did mention that the causes of dilution also include poor management and shortcomings in the know-how. So the question is dilution control given the attention it deserves and support in industry?
I think in some cases it is, in some cases it isn't. If you're in a sub-level open stoping environment, it's critical, and it can get out of control very quickly. So I think that, you know, it's a critical area of focus there in most cases. So, you know, the more modernized that you are in that environment, the more you can put focus on it, and you need to know what the impact of it is. I mean, where I showed you that stope that's got 70% dilution, the economic effect of that is disastrous on that stope. It makes it completely unpay. So this is, why are you there? What are you doing? You know, so get it right for the next stopes. So there needs to be a strong focus. I think in things like our tabular environment, there's a bit of a laissez-faire approach, you know, to say, well, that's the kind of the way it is, you know. And I think that we'd like to see a lot more focus on dilution control and quality mining and those kind of things, you know, and that's where we need to see where technology can come along and help us.
Okay, thanks, Alastair. So now it's 4:10. On behalf of the SAIM and also on behalf of the attendees, it's a big thank you to you, Alastair, for the highly educational talk. And attendees, thanks a lot for staying until 4:10. It was, of course, a very interesting and a very highly educational talk. So thanks a lot again, Alastair. And this concludes the webinar.
All right, thanks very much. Okay, thanks. Goodbye, everybody.
Cheers.